Hello guys, I hope you all are safe and happy along with your family. Also, I hope that you, wherever you are right now, at this moment, hope you are all safe. Today, I am here to just to introduce you some kind of tools, the digital logic circuit tools. Using such tools, we can simulate our circuitry. Yeah, having said about the tool, mainly I'm thinking to use one of the popular and open source tool being used for simulation of different logic circuits, both the sequential and combinational or even complex logic circuits. And that tool is the name of that tool is logisim, logisim. I'll be sharing the link to download that tool in the video description. And to get familiar with that tool, and on the other hand, we need to get concerned about our examination question or examination problem. So what I'm doing here is I'll be picking one of the problem. Actually, this problem was sent to me, I see in our discussion group that someone is trying to do the problem, but pretty unsure or not in the right direction. So I thought to pick the same problem and use it to solve, or I'll be solving it in front of you in this video, and we'll be implementing it into a simulation tool, and we'll be verifying its results, whether the given design is correct or not. So the problem states that, as you can see, the background of this video is a sequential state machine, sorry, just a state diagram, and you may have been looking into that diagram since the beginning, and yeah, we'll be picking the same one. In the diagram it says, or we are asked to solve the uh, given state diagram to a corresponding sequential circuit using RS flip-flop only. So, today's video tutorial, the content of this tutorial will have solution to this given state diagram into the RS flip-flop sequential circuit, which will be simulated. Okay, so I hope that you are excited to go ahead. Let us recall about the steps we have to go through to implement any sequential state diagram into a sequential logic circuit. So for that, first of all, we need to derive a state table from the given state diagram, and then we'll see whether there are similar state, or the state which possess same properties, and we'll reduce the state if it is possible, and we'll then implement it using the asked flip-flop, and we'll design it, or we'll derive a circuitry. So so with this step, so keeping in mind those steps, let us start for this problem, and we have asked to uh, implement this state diagram into a sequential logic circuit using SR flip-flops. So so let's continue. So I'll put this guy aside. I'll keep this uh, diagram on the corner, on this side, and let us draw a state table. Okay, so state table, in any state table we need to state, first of all, the present state. Okay, so as I see in the problem, we do not have any outputs, we just have input, and let us assume the variable x, or let us name this input with a literal x, and let us continue with that way. And here we have altogether four states. So since we do have only four states, for that we just need two flip-flops. So two flip-flops are sufficient for producing four state, or we can design a state machine with total altogether four states with two flip-flops. So if we have states uh, about 8 or less, then we need to have three flip-flops. And if we need to design sequential circuit for the states up to 16 states, then we need four flip-flops. So the number of flip-flops depends upon the number of states in the state diagram. And we clearly see that we didn't have to make any reduction in the. So let us continue. Let us first derive the state table, and then let us continue that way. So while writing or while solving a similar kind of problem in your board exam, you must have to write something. You just can't draw the state table on your paper and then just move deriving the state table. Before that, it is necessary to write something, or it is necessary explaining or keeping some text about what I am doing, or what is the next thing I am doing, or what is the purpose to do this. So I will not be, or I may not be making a uh, complete text, or I may not be including complete text, but uh, just I'm recommending, or I am promoting the habit of including some text uh, in any kind of solution. So here we do. Let us derive state t from the given di dia diagram. So let's derive the state table, and for that, so I'm gonna draw a table, right? So this is let us I'll be writing it on shortcut, because writing on this online whiteboard is too much painful. So I'll avoid maximum text as much as possible. So let us first make a table in here, right? So this the table goes, that is, I will name them gradually. So this is I will say it okay, I will say it. I'll even change the text size. Okay, so I'll say current current state. So we say that current state is a in our term qt, right? So I'm gonna name them current state, and I'm gonna name them later on. And I another we have another thing is input, right? Input. So input, let us assume x is a literal we're gonna use uh, indicating our input. So I'm gonna draw a vertical line from here. Oh, sorry. Okay. Oh, it goes again that way. So this is our current state and input, and I'm going to separate it to. Okay, I think I think drawing through mouse is so much painful, but also you don't laugh, you guys do not laugh on me, right? Okay, so uh, let us give the states, or we have to give we have to assign literals also, we have to assign variables also. So that's why I'm assigning variables here. So we do have two, as I said, that we need two flip-flops for implementing the state diagram, which has total altogether four states. So that's why I am giving a a is the output to flip-flop 1, and b is the output, b will be the output to flip-flop 2. 2 or second flip-flop, and x will be the input. So I'm again going to write x in here. So just to fill the table column or table row, or sorry, the table cell, and I will lock it down in the same way. So in the other hand, this is the current state, and I am again in the next column there will be, I'll be listing the next state, right? Sorry, the text are too high to, I'm gonna write it to maybe 12, I guess, right? So next, and we do have our common convention that qt plus 1, that means next state. The t means the current time, and t plus 1 means the next time or next sequence when the clock pulse has been just applied to flip-flop inputs. So this is next state, and yeah, on the next state also I'll be writing here okay, let's go to 20 again, and sorry, I'll be writing here a and uh, b. All right, so we do have the next state too. So I'm gonna again draw a vertical line over here, and that's it. So as we know that I will be drawing here 8 lines. One. Current state, let's say we start from 0 and then again 0, and from state 0 0 at input 0, we have next state 0 0. So when there is when the output of the flip-flops are at both are at 0 0, and when we apply 0 to the input, and upon next clock pulse the transition does not happens to any other state, or it doesn't go to any, it doesn't jumps to any other state. It rather it jumps to own state. So own source state, let's say source and destination, so own source state. So 0 0 to 0 0 when x is 0, and again 0 0 to 0 0 to 0 1 when uh, input x is 1. So when there is in state, when the state is at 0 0, and when there is 1, uh, then uh, uh, then upon the next clock pulse the state goes to the destination state will be 0 and 1, 0 and 1. So in the same way, from 0 1 1 8 0, it stays to 0 1, and from 1 from 1 0 to, sorry, oh sorry, so from 0 1 at x equals to 1, at x equals to 1 it goes to state from 0 1 x equals to 1, it goes to state 1 0, right? So you all can see that. And from 1 0 at x equals to 0, it goes to, it remains same, so that means 1 0, right? And again from 1 0 1 0 to when x is 1, uh, it goes to another state, that is state 1 1, and from again 1, sorry, from 1 1 8 0, it stays to the same state, that is 1 1, and from 1 1 at x equals to 1, it jumps to state 0 0. Okay, so we derived this is the state table from the given state diagram. While we derive that, and we just have this information from the given state table. So our job is to now implement SR flip-flop, or we just need to implement or we just need to have some way here to use RS flip-flop to make this state table or state diagram happen. So the our way, or the way to do that is we will refer to the excitation table, right? And we'll refer to the excitation table, and we'll uh, use that excitation table to act the given flip-flop, or to accommodate the given flip-flop into the given state machine, or state diagram, or state sequence. So so first of all, let us let me bring the state table for RS flip-flop. Okay, okay. So let's I hope that this will not crash. Anyway, okay, so we've got that. We have got that, and oh, this seems to be a little bit blocking over here. Okay. So I just need this part. Let us keep this aside. Okay, so I think we are okay to go. Okay, so this is the state. This is the excitation table, guys. If you can see it, I don't know whether it is visible to you or not, but let me highlight it. Okay, so this is our excitation table for the RS flip-flop. So what excitation table tells to us, or what is the purpose of excitation table is to let you know, or let us know that when at certain input, when there is clock applied, or from, let's say, uh, the flip-flop output is at state 0 at the moment, and when it goes to output 1, and what needs to happen at its input, or what are the changes, or what are the input that should be supplied before the clock pulse is given, or what are the values that should be loaded at input, and then after trigger the clock, so that in the same way the output will change. So that is the main significance of the the excitation table, and that is why the excitation table is most useful thing at this moment, or we need to have the excitation table to implement this given state diagram into the sequential logic circuit. So okay, so let us proceed. Let us not waste our time, let us proceed. All right, so I'm gonna give the name again in here. Let's reduce the font in here, and the name will be okay, so the next state means flip-flop input, right? Oh, sorry, flip-flop inputs. We're gonna use flip-flop inputs. Okay, so flip-flop inputs, that is oh, why this is not happening? Okay, I just changed the color, but why it is not changing? I'm not sure. Okay, flip-flop inputs, I'm gonna give the name this way. So this will be input to the flip-flop A, let's say, RA, I'm gonna write RA, let's increase it to 20 again, RA, and then S A, or okay, let's make it easy, let us use S in the beginning. Let us use S in the beginning, SA and RA. Okay, so I'm gonna close this. This is for flip-flop A, and again I'm gonna use, again SB and RB. Okay, I hope that you are you are understanding what I'm writing on here. All right. Oh my god, oh my god, I hope that you are getting to me. So I'm going to erase unnecessary lines over here. So I'm gonna remove this because this seems pretty useless, isn't it? These guys are outputs, and oh sorry, so it is, these things are outputs, and in the same time these S and R are inputs, because what this table is, what this excitation table tells tells to us is, uh, at the given output what should be there in input. So that is the main significance. So I'll be writing here. So when there is, let's say, zero, sorry, when there is transition from uh, 0 to 0 and 0 to 1, or 1 to 0, or 1 to 1. Okay, so when from output to change from 0 to 0, so the flip-flop never be on set, so set is always 0 at this moment, or and from since the last output is 0, so there it doesn't matter whether the reset is 0 or it is 1, so we put don't care in here. And from going from 0 to 1, so set should be 1 and reset should be obviously 0, and from going 1 to 0, set should be 0 and reset should be obviously 1, and from going 1 to 1, so set is at don't care position and reset is at 0, because there shouldn't be any reset at that moment. Okay, so let us continue. So from we will relate this in here. So from 0 to, from current state to next state, from current state to be at 0, to next state to be, from current state at 0 to next state to be 0, the flip-flop inputs, let's say we are dealing with A, right? We are dealing with A, so we should take care of SA, right? So the SA and RA are input to the A flip-flop. So from 0 to 0, there is what is there in the excitation table? 0, don't care. So what we'll write here, we'll write 0, and here we'll write don't care. Okay, uh, okay, okay, 0 and 0 and don't care, right? So from again 0 to 0 we will go 0 and don't care, and again from 0 to 0, right? It goes the same way. Oh my god, from 0 0 0 0 0 1 0 1 0 1 0 1. Oh, so it's something missing. From 0 0 to, okay, let me see it again. 0 0 to 0 0 0 0 to 0 0 to 0. Oh, 0 1 to 0 0 0 to 1 0 1 0 1 to 0 0 1 to 0 1 0. Sorry, there is a mistake in here. Oh, okay, okay, okay. I need to erase it. I need to erase it. Sorry, sorry. Okay, 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 okay. This eraser is so much messy. So from 0 1 to 0, from 0 1 to 0 it goes to 1 0. So from 0 1 to 0 it goes to 1 0. I think I need to erase both of these. From 0 1 to 0, from 0 1 to 0, from 0 1 to 0 it goes to 1 0. So we have to write from 0 1 to 0 it goes to 1 0, and from 0 1 to 1 it goes to, from 0 1 to 1 it goes to same state, right? 0 1. Okay, okay, okay. So okay, we are here. So 0 0 0 to 0 0 don't care, and 0 to 1 what we have? 0 to 1 we have 1 0. So we're gonna write here 1 0, and from 0 to 0 again it goes 0 and don't care, and again 1 to 1, right? 1 to 1. So we have the option from 1 to 1 we will write 1 to 1 don't care 0, and 1 to 1 again uh, don't care 0, and 1 to 1 again don't care 0, and at the end 1 to 0, right? 1 to 0 means 0 1. Okay, 0 1. On the same way we'll go for another flip flop, right? So that is second for B. So 0 to 0 we go again 0 don't care, right? And again 0 to 1. So 0 to 1 it goes 1 0 1 0, and 1 to 0 1 to 0. So 0 1 this time, 0 1 1 to 0 0 1 1 to 1 1 to 1 don't care 0 1 to 1 don't care 0 1 to 1 don't care 0 0 to 0 0 don't care, right? 0 don't care, and 0 to 1 0 to 1 is 1 don't care 1, sorry, 1 don't care, and 1 to 1 don't care 1, sorry, don't care 0, and 1 to 0 1 to 0 is 0 1. Okay, okay. Oh, is there any 1 don't care situation? No, no, where we have done slightly silly things in here. So this is 1 and 0 1 and 0, sorry, 1 and 0. So don't care 0 0 1. Okay, so we have now derived, or we are on the way to implement RS flip-flop for the given state diagram. So we do have our state table is now ready. So our next job is to, our next task is to uh, uh, implement it or reduce the given inputs, or these SA, RA, SB and RB are outputs of the combination logic, and A, B and X, these three things are input to the combination logic. The combination logic will provide appropriate combination uh, for the flip-flop inputs so as to generate the given sequence, so that flip-flop acts in a way that will make this sequence to happen. So let us move ahead. I'll switch to next page, and then maybe I will draw the K map. I will start drawing the K map, right? So I'll not be using any text based things in here. So we need four columns in here. Sorry, four columns. Okay, so let us see. For this is for SA. S A, let us say that, and this is A, B and X. Okay, this is 0 1 0 0 0 1 1 1 and 1 0. Okay, so let us go to the again page, previous page, right? So we have 1 8 0 1 0, right? 0 1 0. For SA we have 1 8 0 1 0 0 1 0 0 1 0. So we have one only this at this place, and we have uh, no another one in the no one another one. So we see the don't care now. So 1 0 0 1 0 1 and 1 1 0 1 0 0 we have don't care, 1 0 0 don't care, and then maybe 1 0 1 and then 1 1 0, I guess. 1 0 0 1 0 1 and 1 1 0, yeah. So 1 0 0 1 0 1 and 1 1 0. Okay, so so from this we can see that we can make a pair. Okay, so this this only seems the appropriate pair, because there is no reason to use this one. So I'll just encircle this one at this moment. So we have that S equals to, what is our result then? S equals to okay, S equals to bx bar, right? So S equals to bx bar. Okay, that is fine. Again I will go for another flip-flop, right? Sorry, flip-flop input. So okay, 1 2 3 4, right? So and then the same things in here, A, B and X. 0 0 0 1 1 1 and 1 0. This is 0 and this is 1. This is for RA. Let's say for, let's finish for flip-flop A. Okay, and okay, for RA let's go to the last page. For RA, what we see that don't care 0 0 0 don't care, 0 0 1 don't care. Okay, 0 0 0 don't care, this is don't care, and 0 0 1 also don't care. Again we move backward, and sorry, so what we see, 0 1 1 don't care, 0 1 1 don't care, and the 1 1 1 last one is 1. 0 1 1 don't care, and last one 1. 0 1 1 don't care, 0 1 1 don't care, and 1 1 1 it has 1, other all 0. Let me confirm it. Yeah, 0 1 1 don't care, and 1 1 1 only 1. So okay, so in this case also we see that we just have this guy, we can only make this pair, right? So we do not have any other option left. So Yeah, so then we have our output is let's say this is reducing it, it's just bx, right? It's just b and x. Okay, so bx will be the input to the r of a flip-flop. Okay, so moving on, we'll again go for another key map, solving another key map. Okay, so okay, or I think I should skip this, right? Because you all can do this, isn't it? So okay, so I'll just skip this and I'll just take take a small time and I will uh, write the final expression. Now you guys do it on your own. Okay, so moving on to the last page, moving on to this page, so we have SARA and okay, I'll go for SARA and another is SB, right? SB equals to okay, let me make a small calculation and get back to you. Sorry. Okay, so SARASB, SB seems to be B bar X, B bar X, and what is another? RB, right? RB is A bar X bar plus A B X, right? Okay, guys. So this is the we just solve for the combinational circuit that will be input to the flip-flop input lines. The flip-flop input lines are R and S to SR flip-flop. So let's move to another page and we'll continue from there. Okay, so uh, summing all things together. So SA equals to BX. So I'll be writing in here that in text. So SA equals to BX bar. Is that correct? Okay, that is correct. And SB, sorry, RA equals RA equals BX and SB equals B bar X and RB equals A bar X bar plus ABX. Okay, so we do have all four inputs. Okay, so let us see, now let us implement it. We can make this circuit, right? So let us implement it using one of the tools. So I will introduce you a tool very shortly. Okay, this is the tool I'll be showing you, right? So this is the tool, this is called logisim, guys, and this is very awesome tool. And if you google it, if you google about logisim, then you're gonna have a lot of uh, resources about it. It is used to simulate a massive complex circuit too. Even I found that even different digital signal processors and different complex arithmetic logic units or different complex logic blocks has been simulated, or this tool is being used to simulate complex logic diagrams. So this is pretty handy, and this is open source tool. And if you go and see to the help and see tutorial, so you can find a complete tutorial on it. Um, just let me scroll over through it, so you can see how to use this, right? and soft circuits. There are different things, wire bundles. I also do not know about all these things. This is your duty, or this is your task to explore about all these things, and during this vacation or during this lockdown time, right? And you'll have in-depth knowledge of this tool, or you will have no problem if you design any of the logic circuit in future and need to verify or need to see whether it is working or not. So let us continue. Okay, so here are different in this pane or in this panel we see that this is on title. Let us save this, right? So let us save. Okay, let us save and give a name. uh, to question one, right? Okay, so I just saved it and we have the main page. I don't know, giving a name, but let's go straight forward. So our task is to implement the given state diagram, or our task, we have derived this Boolean expression from the given state diagram, and we need to implement uh, this Boolean expression into a combinational logic, giving input to flip-flops so that we'll achieve the given will creator will have a logic circuit to the state diagram uh, given in the question. So let's move forward, and maybe you can note down this expression. So SA equals to B x bar, RA equals to BX, SP equals to B bar X, and RB equals to A bar X bar plus ABX. So I will now be fully working on this logisim tool. So okay, let's get started on this. And here we need to have two flip-flops. First of all, we need to have two flip-flops. This is SR flip-flop, right? So I'm gonna use SR1 in here, and again SR1 in here. Over here, guys, I don't know, I don't see any grids in this tool. I don't know how to enable plain template intentional. I don't know, language, layout, printer view, show attribute. I don't like this. First radix when wire port after reading component, sign decimal. Okay, this is not useful. Okay, so what we need are S equals to B x bar, right? So let us assume this is flip-flop A. I'm gonna give this flip-flop A, the name A. Okay, and this is flip-flop B. So this is the output A, and this is output B. Okay, so I'm going to label it, or there is no way in labeling it, so there is an option in here. We can use tunnel. So tunnel is a connection or a convention. We use it for making virtual connection, okay, or to indicate it also we can use it. For example, I will be using this tunnel. You'll understand one by one, just not worry at the moment. So I'm gonna give this label A, right? So this is output from A flip-flop, and this is output from B flip-flop. This is just a tunnel, means this is just a labeling, a way of labeling, which will be useful in making connection to other portion of the circuit also. And what we do have the output A and B, right? So, and we need another input. X is an external input to X is an external input to our sequential circuit or the circuit we have designed. So I am gonna use the tool or the option or the component pin in here. So I'm gonna name it X, right? So I'm gonna label it X. Okay, so we have X, A and B. we all we have now all three variables that we see in our expression, right? So what we need first of all is SA equals to B X bar, right? So this is a flip-flop and SA means this particular input, right? So SA means when I zoom it, and SA means this particular S input of a flip-flop. So SA equals to, what we have is SA equals to B X bar, right? So B X bar, that means B is ANDed with, sorry, B is ANDed with X bar. So what we need is gates right here. So AND gate, I'm gonna take one AND gate, and how many inputs? I just need two input AND gate, right? So what should be in here? Okay, so yeah, this is AND gate, and you see that there is different colors to the gates, right? The output is red, both the inputs are blue. So when I choose this uh, change value within circuit tool, and when I see this is don't care, this is don't care, and this is E, that means error. Okay, so there is no input supplied, or the software tool says that there is error in output, or we need not have to care about it at the moment. So let's leave about this, guys, and let's move forward. So our job is to connect as per we have derived the boolean expression. So let's continue. Let's not waste our time. We already have uh, wasted a lot of time. So what I'm gonna do is, okay, I'm gonna finish this wiring first. Okay, so this is I'm gonna finish this. And what is in our circuit is, sorry, this is B X bar, right? B X bar is our input to SA. So let us say this is B, right? Let us say this is B. I'm gonna use again a tunnel. I'm gonna move it to west, and this is, I'm gonna label it to B, right? Okay, so B X bar. This is X. This is X, and we are looking for X bar. That means what we need a NOT gate in between it. So I'm gonna use the NOT gate southward, right? And I'm gonna use it. Okay, so this is X bar, right? So B X bar, we have B and then X bar, which is applied to the A flip-flop, S input of the A flip-flop. So what is the R input of the A flip-flop then? Let us see that. Bx, right? So Bx, just Bx. So let's move this guy little this side, so that we will have room to draw the line. Okay, okay, I think I need to delete this. I need to redraw this. And another is, again, uh, okay, so what is that for? This doesn't have any grid system, so that is ridiculous, guys. B bar X, that is B bar X. So I'm again in need of NOT gate. So NOT gate, I will south. Okay, that is fine. Okay, NOT gate. So what is BX? b bar x, oh sorry, b bar and x, right? So okay, b bar and x. So let's put this guy again, this same, b bar and x. So I'm going to delete it. Again, delete it. B bar. This is b bar. X. Okay, so this is x, right? Okay, b bar x. Uh, let's do this. Okay, so this is pretty not tidy, and I'm gonna delete it too. This is b bar, right? B bar and x. X. So I'm gonna draw a line from here, and yeah, this is much more tidy. Okay, so b bar x for we have done for flip flop 1, and for flip flop 2 this is oh, ra equals to just bx. Sorry, this is wrong. Just bx. Ra equals to just bx. Okay, just bx. Okay, that is fine. R equals to just bx. And again, let's move for another flip flop, that is rb equals to a bar x bar plus abx. A bar x bar, right? A bar x bar. We need another AND gate again. So I'm gonna put it here. I'm gonna put it here. And a bar. What is the SB equals to b bar x, right? B bar x. Okay, we're gonna need the bar at this b bar x, x and b bar and b bar. Okay. Not good. Okay. I'm going to delete this. I'm not liking it. B bar x, right? B bar and x. Okay, that is fine. B bar x, that is s input, right? And another is a bar x bar. So you guys might be wondering, okay, so how this b and this b works together. So okay, let me give a short break. So when I click on this, you see that this is highlighted. Okay, so b, this is highlighted, both all are 0, right? This is also 0, this is also 0. Okay, so these are connected. So that this proves that these are virtually connected, or this is connected internally by the software, so we need not have to worry about it. Okay then guys, I will be continuing, right? The next thing to do is a bar x bar abx, a bar x bar. So we are going to need another AND gate with 2 input, and again another AND gate with at this time 3 input, right? So the 3 input AND gate, we don't know what to do. The 2 input AND gate is a bar x bar, so a bar, right? We're gonna need a this time, so I'm gonna again use tunnel and a, right? A, and I'm gonna not get a bar. Okay, a bar, right? A bar and x bar. Where is x bar? Oh my god, this is there. Okay, I'm gonna pull this guy a little over there. I'm gonna pull this a little over there. A bar x bar, right? Okay, a bar x bar, and then I'm gonna label this a. Okay, so this is no more error, a bar x bar. And the next thing is what we gonna need? A, B and X. So A, where is B? There is B. A, X, where is X? This is X, right? X, A, and let us use again tunnel. And the B seems quite impossible, right? So this is B again, and I'm gonna use this, right? So A, B, and I'm going to use again OR gate, or we need OR in here. Okay, so okay, this is 5 input again, so we need just 2 input. We are not that much great in our design, so we just need 2 input. This software should understand, isn't it? This is not a smartphone anyway. So okay, we've done now. I think we've done. Okay, I'm gonna put this guy a little side and this side, and I'm gonna supply the clock. So this is synchronous, right? So in synchronous we do have clocks connected to the same in all the time. So keep that in mind, guys. And I need wires, and I need again another input. Okay, so I'm gonna make another input. This is, and I'm gonna give a clock in a momentary way. Okay, so momentary way means I'm manually pressing the button, and that will be that will act like a clock. Okay, so because when we see the flip-flops, this is rising edge and both the flip-flops are rising edge, so I'll be providing rising edge in any way using this input. So I'm gonna label it, I'm gonna name it CLK. Okay, that's fine. Okay, so to view the output, what we're gonna do is we're gonna use lead indications to see whether our states are working or not. So I'm gonna use leads. Okay, so let's say this is for A, and this is for B. Okay, so this is for, let's say, A, and this is for state, this is state B, and I'm gonna connect them. Okay, so A to state A and B to B to state B. Okay, so so now our circuit is done, our circuit is built, and let us simulate, guys, so we can have a real fun now. Okay, what was the question given to us? What was the problem given to us? So so this is the problem given to us, and we will investigate whether along with that problem our circuit is working or not, right? So guys, so this is input and this is clock. We just have control whether to our input or to our clock. So let's go. So this is X. Okay, so X is the connection of X inputs, we can see this, and connection of B inputs we can see at different places, connection of A we can see at different places, and B same time. All right, so sorry, so we're going to simulate. Okay, so when there is yeah, both the LEDs are not glowing, or in other words, this input A is at 0, you can see that, and B is also at 0. So at this time we see that the state machine, our sequential machine, is at state 0 0. So when the input is 0, now when the clock is applied, so there will be no change, right? There will be no change. But when the input is 1, when the input is 1 and when the clock is applied, so there should be transition from 00 to 01. So let us give a clock. Okay, so you see that 01. Okay, so A being 0 and B being 1, because B is least significant bit in here, so it is 1, right? So when X is 1 and this state machine is at state 01, so in this state uh, X is 1, when input is 1 and when the clock is supplied, so that at that time there should be no change in state, because at 1 it remains at 01. So I am changing the clock, so there is no effect, right? And when I again change the input to 0 and when I give the clock pulse, this state machine should have a transition from 01 to 10. So when I give the clock pulse, and you can see that it goes to 1010, right? 10. So when the X is 0 and when I supply the clock, so there should be no change in state. So you see that when the input is 0 there is no change, and when I again sorry when I again use input 1 and sorry when I again supply 1 to the input, and when I uh, give the clock, when I again trigger the clock, and there should be change. So when from it is a state 10 and I have supplied 1 to the input, and when I push the clock or when I trigger the clock, so there should be transition to 1 1, state 1 1. So okay, so you can see that there is state 1 1, and when from state 1 1 when there is input 1 and when I again give the clock, so it goes to state 0 0, right? So when I again give the clock, it goes to state 0 0, and from 0 0 when the input is 1 it goes to state 0 1, right? 0 1, and when there is 0 1 when the input 1 is given, it stays at the same state. So yeah, we can see that, right? So this is all about today's session, and I'm just trying to give you how to design a circuit using different flip-flops, whether there is SR or JK or T or T. That is you should follow the same way, same steps to derive the sequential circuit. And if you like to simulate either a sequential circuit or combinational circuit or any other or any circuit belonging to either combinational or sequential or combiningly both one, then you can use this tool. This the name of this tool, maybe I will put the link or the description in the video description, and you can follow that link, or at least you can push me a message, and uh, either way. So this is the way you can do it, or you can simulate, or you can see how your circuit works. Okay, so during this time it would be even beneficial or even great if you use this tool to verify all of your problems, for example XS3 to BCD converter, or gray to BCD converter, or let's say the ripple carrier circuitry, or things like that, right? So so I recommend, or uh, I ask you all guys to uh, get interactive or get involved in these sort of activities, and I'll be soon uh, sharing you other useful materials, uh, and you can keep yourself engaged in study stuff. So that's all for today, and this tool you can even use, uh, talking a little bit about these things, you can even use, we have 7 segment display, LED matrix, and even you see that there is an LCD device, so you can even use this tool for you can even use this tool for designing a digital clock. Back in my college days, when I was a student like you, so I also had designed a digital clock without using any of the programmable chips. Okay, so uh, you can also do that, and you can even do better than that. Okay, so for example, you can design let's say an 8-bit ALU, or even a calculator, or something like that. You can google it, or you can discuss about it, and if you like to do, I will be there supporting you. So okay, so let's wrap up for today. That's all. And yeah, see you. Stay safe.